Hello, good morning, everyone. Uh, Happy Independence Day to all of you. क्या कर दिया? Hello, we welcome you today for our next session. And I hope you can hear us. Just write in the chat if you can hear us. And yes, okay, good. So we'll be starting soon. We have certain announcements. We have created an email ID which we have put it in the chat window as srishriastro2020@gmail.com. So we'll have a correspondence through that now. The poll suggested that many people want to use Telegram rather than WhatsApp or Slack or any other thing. So we'll start making groups on Telegram, and it's a simple app exactly like WhatsApp. So you can download it and install it on your phones or even in your systems. Third thing, your assignments of Python or any other assignment, please send it to the new Gmail ID which we have created. And what we have realized is there are some people who are even having issues with installing Python and running it. So those who are actual newbies, absolutely new to Python or programming, if they want special sessions, separate sessions, we can have those on other days other than Saturday, Sunday. So do write to us, and we can have smaller groups where we can help them install and run small programs and go ahead with it. We won't be having it on Saturday and Sunday because there are some who are experienced programmers, and for them we have to proceed ahead with our schedule. So, do you want to say something? Yeah. So let's start with the lecture for today. We'll be talking on virtual observatories and its tools. And after that, we will have demo of these things of individual services. Hello, I am Najam Hassan from Mano, Hyderabad. Today I'll be speaking on virtual observatory and its tools. Astronomy has changed over the years from a data poor to a data rich science. We live in an era of big astronomical surveys. We have the 2DF Galaxy Redshift Survey. We have SDSS, the Sloan Digital Sky Survey, Deep 2 Redshift Survey, SAGES Legacy Survey, TUMAS, Gaia, and so on. It has become essential for astronomers to handle the big data sets and interpret the complex astrophysical problems by using sophisticated statistical techniques and technology. From getting data to getting science out of it, we go through a series of processes. We have the data, collected from various satellites, various observatories, and so on. From this data, we select what we are interested in. We have the target data. We do some processing, pre-processing to get some processed data, apply transformations, analysis, and see patterns in it. And we interpret these patterns to get knowledge. To make this process simple, virtual observatories is playing a very important role. So before we come to that, what is Astronomy Data Archive? Astronomy data archives are organized, systematic ways of disseminating information about the celestial objects. Today, these archives are into terabytes or sometimes even to petabytes. So, International Virtual Observatory Alliance was established in 2002 to facilitate international coordination and collaboration for enabling global and integrate access to data gathered by astronomical observatories. These virtual observatory members are Argentina, Armenia, UK, Australia, Brazil, China, Chile, Canada, European Space Agency, European Virtual Observatory, German Astrophysical Virtual Observatory, Hungarian Virtual Observatory, Japanese Virtual Observatory, USA National Virtual Observatory, Observatory Virtual France, Russian Virtual Observatory, Spanish Virtual Observatory, Ukrainian Virtual Observatory, Italian Virtual Observatory, and Indian Virtual Observatory India. The Virtual Observatory is a collection of interoperating data archives and software tools which utilize the internet to form a scientific research environment in which astronomical research programs can be conducted. A virtual observatory is a collection of interoperating data archives and software tools which utilize the internet to form a scientific research environment in which astronomical research programs can be conducted. As a real observatory consists of telescopes and each observatory with a collection of unique astronomical instruments, the bureaus consist of a collection of data centers, each with unique collections of astronomical data, software systems, and processing capabilities. The main goal is to allow transparent distribution and access of data worldwide. This allows scientists to discover, access, analyze, and combine nature and lab data from heterogeneous data collections in a user-friendly manner. The International Virtual Observatory Alliance is a standard body created by the virtual observatory projects to develop and agree the vital interoperability standards upon which VO implementation is constructed. I would like to give a slide on Virtual Observatories of India. The Virtual Observatory of India project is a collaboration between IUCA and Persistent Systems Limited, Pune. This project is supported by the Ministry of Science, Technology and Innovation and focuses on astronomical analysis and visualization. The notable tools developed by BO India is BO-Plot, Mosaic Surveys, and BO-Stat. BO-Stat has been developed along with collaborations from Penn State University. So BO-Stat is a simple user interface and a few R routines for astrophysics. As we proceed ahead, we will see these in detail. So VO basically is interested in doing multi-wavelength astrophysics, archival research, survey astronomy, temporal astronomy. The basic aim is to create a platform where all these things can be done in a simplified way, and the tools would be available for everyone around the world who are interested in using these big data archives. VO project plan is to create these tools for research ADS archives, VizieR and data archives, tabulations for which they have developed the Topcat, and visualization of these objects, which is the Aladin. And like I mentioned, there's interoperability. There's a connection. All these things talk to each other, and data can go flow from one application to another, and so on. The bio innovations are the FITS data format. Yeah, FITS stands for Flexible Image Transport System. They have defined protocols like Simple Image Access Protocol, SIAP, Simple Spectral Access Protocol, SSAP, Astronomy Data Query Language, ADQL, BO table formats, and table access protocols. So essentially, BO defined protocols, defined rules so that images can be transferred from the observatory to the users in certain specific formats, in standards, which lived up to certain standards. Same way, rules of sharing data in tables, rules for defining query languages, right? Making a platform which is simple and accessible to all, right? And also have certain standards and protocols for how to access tables and so on. The tools which they have developed are extremely useful, and as we proceed, we will see these in particular. We have VO table, which displays and analyzes the tables, VO plot in Topcat, we have VO stat, we have Aladin and ESA Sky used to display images and for analysis. We have VO spec and VO and spec view. These are the standard display tools for downloaded data spectrum and for the analysis. Data visualization tools like Aladin, it's an interactive software skies atlas. Skyview, it's used for generating images of any part of the sky at wavelengths in all regime. Topcat, which is an interactive graphical viewer and editor for tabular data. VioPlot, a tool for visualizing astronomical data. VioMegaplot, for handling large number of points and range of millions, similar to the VioPlot. And both these tools have still common functionalities. Stills, processing of tabular data, the packages has been designed for, but it's not restricted only to astronomical tables, such as object tables. VioConvert, a tool for converting files from one format to another. It supports following file format conversion: ASCII to VO tables, FITS to VO tables, and VO tables to ASCII. So let's now look at some of the VO tools. VioPlot, for example, it can be downloaded from the site specified here. If you click it, we will go to the site, and You can scroll down and we have VOCat, VOStat, and so on. And we have VOplot for plotting VO tables. So these are all the different versions. So VOplot1 a.zip with the user's guide. When was the release? The release dates are here. And don't take the beta versions, take the ones which are tested. And you can download this file and install it and run it. So when you unzip the file and run it, you'll get an interface of this kind. This button helps you open a file either locally from your computer or from a URL or from some other location. For example, uh, I've downloaded the zip file, blew it up, and we have a VO plot here. And uh, here it is. I can click and specify which file name we require and which format we need. So I have some sample files, DSS file, and it gives you the table metadata. What are all the different rows and columns? And you can do plotting. You can change which row against, we have RA versus DEC. You can change to proper motions and plot. You can make it a log plot. You can reverse the scales if you wish. And you can download it in the whichever file format you require. You can save this file and so on. Similarly, you have the cone search from which you can get from the net. We have histograms which you can plot and 3D plots. You can look from different angles. So you can do this with data sitting on your system, your own data files, or files of catalogs which you can get from the net using the different tools. So it's most important that you try these things and download it, unzip it, and look around with this. Coming to Topcat, again a very versatile tool. With click of buttons, you can load data, analyze it. This is the site from which you can download Topcat. And here it is. What is Topcat? The features, screenshots, and you have downloads here. You can go to the jar file. You have Topcat full jar. You require Java Gate to run this, or this is a Topcat Lite. And again, I'll give you a glimpse of how this works. And I have it downloaded here. And Topcat, when I click it, it runs. I open a file. I decide which file I'm looking for. Either I look at the file for a file which is there on my system. I have to specify. If it is not fits file, you'll have to specify in which file format it has. These are all the different file formats it supports. For example, the file which I have here is comma separated variable, and I say, okay, I can see the file. It's a simple file which I just made to show you. It's a 3-column, 10-row file, and I can do scatter plots. So I can take what is on the x-axis and what is on the y-axis and plots here. I can add forms, add line to it. I can choose the font of these points, colors of the points, sizes, and so on and so forth. We can do histograms uh, for whichever. We can do histograms and so on and so forth. We can see the statistics of the file. It gives you a big brief summary. For the first row, the mean is 5.5, standard deviation is 2.87, minimum is 1, maximum is 10, and so on for the second row. And extremely useful and versatile application. I can open another file and I can look at the other file too. And this is to match the two. You can define functions, you can plot. So when we have loaded these two tables, I can do a matching and so I specify which one I have, um, which are the two files, and when I match them, it shows you there are 7 pairs found which are same. It creates a new table, match table with table 1 and table 2. And this is the table of match data. This is especially very useful when we have very large tables with thousands of rows and columns and you want to compare how many rows are similar or so on. You can define subsets from this, have multiplots and various things, which we shall see as we proceed ahead. So going ahead with the next one, VioStat. There are 2 versions. You can download it from VOI India, the same site which I had shown for VioPlot. But to run it locally, you have to install R. The other easier way of doing it is to use this VioStat, the web service. So VioStat web service is a statistical web service that lets you analyze your data without having to download or install any software. One has to upload the data to the VioStat server at Penn State University and download the results. So here's the link to that location. You open it and you go to the Penn State site and you can start using VioStat right away. There are data and tutorial codes, various things, right? So if you just click on start using VioStat right away, it gives you an interface of this kind. First step is to load data. Next, you select analysis, specify what details you want, and then you inspect the output and download it in the required format you want. So either you can download data from a URL, from a local file, or from SAMS. It talks to the other viewer tools like Topcat, VioPlot, VizieR, Aladin, which you shall see. So suppose we go and choose a file, and say for example I have M file for M3. It's a comma separated variable. So I specify what type it is. Then I proceed to the next step. It has downloaded the data and has given, yes, it has RA, deg, parallax, proper motion, and so on and so forth. You can scroll down and select the tool which you want to, which statistics you want to perform. So just as you see, at click of buttons, we can download data. Yeah, the step 2 is to choose the analysis. You can transform the data sets. We have plots and summaries. Which plot do you require? Whether you want scatter plots, histograms, 3D scatter plots, or whatever. And we are plotting this again, RA versus deg. Then you go with the plotting of it, and it gives you the plots, and you can download the R workspace and run it later. You can download the file in PDF or EPS format. You can continue for further analysis, and there are a host of analysis which you can do on this data. Some standard tests, regression. Yeah, you can go and see one sample is Z test, PET, T test, Wisconsin test. Very versatile tool. You can do regression, you can do multivariate analysis, time series analysis, and so on. So extremely useful tool. And as I said, you go to the website and upload your data set from a URL or from your locally sitting in the system. Step 2 is to specify what analysis you want to do. Step 3 is to give the detailed information. Which columns are you interested in, and in what format you want your output in. Next one is Aladin. Aladin is a sky atlas. You can get Aladin from this site. You can either download Aladin desktop, or you can run a preview on your web page itself. You can choose which objects you require, Simbad, Gaia, Tumas. Okay, so if you prefer to run it from a system, you can download Aladin, and I have downloaded it here. Again, you require Java for that, and you just click it, and I'm going to run it from my system right here. This is what it looks like. I can give the command here what object or what coordinates am I looking for. Say for example, I say M13, and it's connecting to the net and getting details. Yeah, so we have this globular cluster M13. It has loaded the DSS image. On the left hand side, it shows you image can be got from 410 sites, how many databases are available, how many catalogs are available, and so on. And you can do various uh, analysis right here. We can stack up different objects from the same region, stack it up and see from different catalogs. So we will see these in detail. It's important to get familiar with it, download it on a system, get different objects, and uh, just look around so that you get, for example, I say M31, Andromeda Galaxy, it is downloaded Andromeda, and so on. You can zoom in, zoom out, and do all kinds of things. And important thing is these catalogs, the sky, these are the STSs, TUMAs, right? From the same region, I can download the STSs ones. I can download the tables. I can use Topcat to analyze it and do a variety of things. Extremely useful. And coming to the next one is VizieR, where you can access the catalogs. And this is the website, a link from where you can go to the VizieR. And again, you can give the catalog name and find catalog. You can choose which wavelength you are looking for. And there's interoperability between VizieR, Aladin. You can cross match. You can do um, plotting, right? So it's an extremely useful and right. So it has downloaded all the available catalogs. You can choose which one you are interested in, and you can select which are the rows which you require, whether you want all of them or you don't want the name and so on, and then you can download it and analyze it. We submit it and download these catalogs and do analysis using VioPlot, Topcat, uh, and so on and so forth. So it's an extremely useful tool. And like I said, there is an interoperability between Topcat, VizieR, Aladin, Simbad, uh, VioPlot, so on and so forth. The data can be shared between the applications. Different applications we use for different aspects of either doing plotting or getting the catalogs, analyzing the data, and so on. Thank you. Hello. Now we stop for a session of question and answers. If there's anything specific you all want to ask, you can do so, but I think it's most important that you download these things. Topcat, Aladin, go to VizieR site and look around and play around with it. And then we'll be able to discuss science cases, right? From the data available, how do we, what are the relevant things which we have to look at, which are the things we'll try to look for correlations or so on. So you all should, we'll be putting up the links of the location you can download from. But the simplest one is you can go Google search. Google search and say Topcat, add astronomy to it, because Topcat can even take you to the comic Topcat site. So to make it easier for Google, say Topcat astronomy or astrophysics, and it'll take you there. Similarly, Aladin, search with uh, astronomy or sky atlas, right? So download it, and like I mentioned, first try with simple tables, simple data formats, and then you should not use it as a black box, right? So if you have a data file which you know, if you plot column 1 against column 3 and column 1 against 5, what should it look like? And see that you're getting the same thing or not, right? Fits format, when the files become extremely large, then fits loads much faster and your analysis can be done much faster in fits format. And we can convert from comma separated variable to fits through Topcat itself, um, or the other way around. Yeah, so uh, it's best you download these things and try it out. If there are any questions you want to ask, we can unmute you. You can raise your hand, or you can ask in the chat box. Uh, Probably while this was going on, you didn't get time to actually download any of these applications and try them out. But maybe by the next weekend, you'll be in a position to have it tried. But all the same, if you have some questions, we will address that. And on 22nd of August, Mark Taylor will be talking about Topcat in detail, right? Yeah, that's next Saturday. So you better concentrate on Topcat for this week. And he's the person who has created it, so he's the right person to give all the nuances and aspects of that. What I have shown you is something very, just the tip of the iceberg, something very simple so that you get familiar with it, right? But it is essential, these are extremely powerful tools which makes research possible. You can find out what catalogs are available on an object, how much work has been done, you can get the cross references, you can get the data, you can analyze this and so on. So you want to say something? Yeah. Yeah, so if there are no questions, are there any questions? Yeah, somebody asked, can R be downloaded on Linux? Yes, R can be downloaded on Linux or Windows or Mac, right? And R, like you all know, it's a very powerful tool to do statistics, and it's free. You don't have to pay anything to get it, and you can download it. VOStat, which I showed you, I showed the web-based service, but obviously you can download from VO India site a standalone tool. But before you use it, you'll have to install R, because that VOStat runs on R. But if you are doing it through the web-based service, which makes it much more comfortable for you, you don't have to install anything. You don't have to have R on your system nor VOStat. The whole thing is done on the Penn State server, right? And we can, yeah, so what do we know from RA versus deck plot? It just shows you the distribution in terms of RA and deck. How are the objects from that catalog or table distributed in right ascension and declination positions in the RA and deck form. Uh, any other questions? Can these be used in a smartphone? No, you can't use this on a smartphone. You have to use a computer, a laptop or a PC. You can't do this analysis on a thing. Yeah, maybe when you are linking up to a server and doing things, you can, but the data which comes in, you can't store it on your cell phones and yeah, so don't do it because you'll not be able to manage that on a smartphone. Uh, can we use these tools in Linux? Yeah, of course. All of these are done. They are done on Linux. Most of the time, astronomers they use Linux because there are certain packages and software which run only in Linux. The ones which we showed here today, they work on Mac, Linux, or anything because these are Java-based ones. But when we come to say IRAF and other things, then you have to do it in Linux or on Mac. And yes, all these run very well on Linux. And I showed it on Windows because most people probably have Windows systems. But it would be a good idea for you to partition your hard disk and go install Linux on one part and work on Linux. Yeah, it's a more secure, stable system, and uh, it's a very yeah. I would advise switch to Linux as soon as you can. How to show error bars in graphs? Yeah, there are ways of showing errors in graphs and so on. We will come to these in uh, detail. In yeah, so as of now, you install these applications and run that. Uh, we can have astronomy data analysis handled on sessions weekdays so we can get a better understanding. Yeah, so Rohit says that if we can have astronomy data analysis hands-on session on a weekday so that we can get a better understanding of analysis, this will be of real help for us. Yeah, sure, we can do that, Rohit. We'll be happy to do that. But initially, you have to install these things. Just try with some data which you can get, and very often small things create problems because when you are downloading a file and you don't specify it as a comma separated variable or tab separated or VO, then you get errors and you are lost, right? And many of these issues are very simple. You just need to realize that yeah, you have to, when you are selecting a file, you have to select the type to whether it's an ASCII file, whether it is a FITS file. By default, if it's a FITS file, then Topcat and all they load it without you specifying it. But if it's anything else, other things which are not by VO standards, then you have to specify it. But as you have noticed, there are many file formats which are available. Yeah, so we can have sessions separately for data analysis during the week. And you'll have to specify which is a good time to do that because some of you would be starting your classes soon. Yeah, or probably would have already started classes in your colleges. Okay, so we can choose a proper time where we can sit. It could be late in the evening too. If you all are interested, will be happy to help you with it. Similarly, as I mentioned, we can have sessions for specifically Python for novices. We can separate it into different groups, different levels of it. Yeah, so Python we started last week. We are going to have another session today, and then we'll have a few more. By the end of it, you would have gained sufficient knowledge. So Rohit says late evening sounds good. We'll check it out with which is most convenient for all of you. Yeah, so we are open for that. Maybe 10 in the night, or we can do that. And it could be a small group too. It needn't be another 100, 200 again. Those who are interested, we can meet in smaller groups so that we can handle their problems and issues. Okay. Yeah, so now I think there are no more questions, so we will continue with today's session. Now, Priya ma'am will come and again demonstrate a little more in detail certain of these tools, ADS, and you're building ADS. Yeah, okay. So I'll hand over to Priya.
So good morning, everyone. This is the one, right? Yeah, okay. So like sir mentioned to you, tomorrow on next Saturday, on the 22nd, we have Mark Taylor, who's the person who's actually written the code for Topcat, who's actually going to be talking to you all, right? And it's really nice of him because you can, I mean, he's in Bristol, in the University of Bristol. So actually 10 o'clock in the morning for him is 4:30 in the night for him. But he himself offered, okay, no, there's no need to change the timing. I will get up in the night and do it. It's okay. So it's really nice of him. I mean, this person is going to get up at 4:30 in the morning to address you all so that the schedule takes place as per schedule. So I really want that we prepare ourselves for the session with him. So I hope you all are all very clear as to how to, I'm going to share uh, how to actually get Topcat. So what you're going to do is, where is your browser? I'll open a browser 1 minute. No, I need the browser. Okay, so what I'm going to do is, yeah. So what I'm going to do now is I'll open the browser, right? So sir had explained to you about how to get Topcat. So you will actually just get Topcat by just saying Topcat. Don't say only Topcat, otherwise you'll get the cartoon figure. So you'll say Topcat Astronomy, right? And this is the thing. Downloading it is very simple because it's just Java based. What is this nonsense? Yeah, so it's just Java based. So you can take this and directly, you will directly download the .jar file. Okay, so you also need to have Java running on your system, and with that you will get this thing on. Okay, now I wanted to tell you all about one thing is how are you going to get the data we are talking about. Okay, so one simple way of getting the data is by using Topcat itself. Okay, so I'm going to you have Topcat running here, right? Where is Topcat? Here. So I'm going to open Topcat. So your homework for this week is to actually install Topcat. Okay. Now for Topcat, when you actually see the data file, if you're loading a table, the table can be of various formats. You can see over here, the formats can be fits, VO table, whatever formats, right? So I'm going to show you how to actually get the data directly from Topcat. Okay. So like sir told you all, there is VO. This is the virtual observatory. That means this accesses you to various VO tools, right? Interoperability, there's a SAM protocol with which this can talk to other VO tools. Okay. So that we won't worry about it today. Let us just look at this VO tool. So let us, for example, take a cone search. Okay. I'm showing you how to actually get data with which you can play around with. Okay. So you do a cone search. Click on cone search. And let's go to my favorite data, which is the Gaia data. So you just say Gaia DR2. Okay. This is the data release 2 of Gaia. Okay. So this would be the key, this thing. Supposing you're looking for Hubble space data, you will write HST over here. Supposing you're looking for some other data source, you will put that over here. And you say find services. So now this is actually looking for where can you actually get your data. Okay. So let's go for the simplest one. This is Gaia DR2 at ESA. ESA is the European Space Agency. That is they have actually set up the satellite. So we can say we want to use Gaia DR2 at ESA. And let us here, for example, let's take there's a globular cluster. It's called M3. Okay. Or you can take any object for which you know the name. Okay, NGC something or whatever. You have to run something called resolve. Okay. Now, you all did not see, but there is something called Simbad. We'll talk about that later also, which actually has a catalog of things. So if I resolve it, you can see for M3, it resolves and it actually gives you the, the coordinates. This is the right ascension and the declination for M3. Okay. So now you're going to look for M3, but it's asking you in what radius, what size do you want it? Okay, so degrees are very large, so we'll go in for arc minutes. Let's say, and this is a globular cluster, so we won't take a very large area. And I'll tell you in advance that this globular cluster is very far away from us. It's 10.5 kpc. It's quite far. And therefore, we are not going to take a very big size. Okay, because otherwise I will get too many objects. So what you do is I've given this thing and I say, okay, for two these things, and now it is loading the data. So this is going to tell you how to get data from Topcat. You can get data through 100 different ways, but this is the one because we are concentrating on Topcat for today. So let us try to see how to actually get data from Topcat. So we, if you remember, we went in for a cone search. After cone search, we actually said the keywords were Gaia DR2. These are the keywords with which we searched. We selected some source over here. Then we gave an object name, right? So we gave the object name to be M3 and we pressed resolve, and resolve actually gave us the position, the RA and deck. And now we are telling it a cone is like a cone. So it, you know, it will give you within a certain size. So you are actually going to get objects which come within that 2 arc minute radius. Okay. Now you can see the number of sources it's getting over here. It's getting a large number of sources. And I should have actually changed the format, but I don't know whether I can change it now. So let me keep the format as fits format. We've done different file formats. So Topcat, like I told you, it's a much more evolved version of what you do with Excel. It's a spreadsheet, but it takes data in different formats. So the formats are, for example, fits format. You have, these are all different formats, plain ASCII format. So if you actually made a text file, suppose you made a text file, right? You can load that text file in Topcat just saying that the format is ASCII format. So just write your things in form of 2 columns, for example, X and Y, and you can load that, right? So we can do that if you want. So here, this is the file. So you can see this is the statistics, the sigma button. If you press this, you can actually see how many objects we have. So we have 5038 objects, okay, in our file. And it's basically telling me what are the columns it has in the data it's taken. This is the distance from the center, the RA, the deck, the parallax, various things, right? So in this way, you have got this data set. You can press this and actually see it in the form of tables, right? So here are your tables. This is your table. Like I told you, if you want, you can even make a plain, um, text document, right? You can make this thing test document. I'm calling it test. And this test document, I can open it. And for example, I can write, oops, sorry. I can write 1, 1, 2, 4, for example, 3, 9, 4, 16. Okay. So I've made this file and I've saved it. If I want, if you don't want to go through the torture of downloading data, you can just make this plain text file. And then here I can say load table. I have to change the format to ASCII format. I can do the browser. And here, if you see, I look for my test file. So my test file is here, test.txt. The table format, again, I can specify that to be ASCII. And that's it. So here you see, this is my test file. So if you don't want to, if you want to start off with a simpler data set, you can start a plain text file and upload this text file. Okay. So let us first look at this text file before we work with the other one. This one is what is called a scatter plot. This one is a histogram, like you can see. So I can make a histogram where I put a histogram of the values we are getting. Sorry. And I can put here, you just put the column 1 is our x's. So we had 1, 2, 3, 4. And column 2 was the y's, right? Again, in this, since this is there is a coding version of Python in which you can do coding, but the beauty, sorry, of Topcat, but the beauty is when you're doing it through these selections. So here you can see that if I want to adjust my histogram, I can do various things. I can put X in log scale, right? I can put Y in log scale. I can flip it. I can change my range. For example, if I want to keep it larger or I want to keep it more, I can put my X range, say, being between 0 to 25, for example, right? Let's say 25. So now I've made the range from this thing. I can reduce the range by doing this. I can bin it like this. I can do that. Since these are, since this is a histogram, I can even adjust the size of my bins, right? I can adjust my form, right? You can see how do I want to display my histogram, as semi-filled, as open, as spikes. It's very, very user friendly, right? So I would advise you all that before next Saturday's class, as homework, you try out all these things, right? And you actually see how to do all these things. You can also, we won't talk about this, but you can also do some amount. So like here you can see your bins. If I want, I can adjust my bin size, right? So I can increase my bin size, I can decrease my bin size, I can do various things with my histograms. Similarly, I can also do a scatter plot of this. So my scatter plot is giving me column 1 versus column 2, right? And you can see that I even have all these different, sorry, I have all these different options over here. I can, if you can go into forms, you can click on form, you can change the form. You can also, for example, do a linear fit to it, right? You can do a linear fit and show your fit, okay, if you want. And we won't talk about fits just now. Let us leave that. So we can look at all these things like this. If I want to keep my if I want to connect my points, I can, you can add a line. Why is it not adding the line? It should add the line. Okay, it's here. It's here. Sorry, I'm clicking the wrong one. So let's go here and let's go here and we can add the line. So this is added a line to it. Later on, we'll see, you can try it out as homework as to how to do a fit. So the fit also can be done from here, where you can actually add a fit. This is a linear fit. You can fit it to a certain function also. You can do all kinds of things, right? So try this out, right, with a simple ASCII file. And now let's look at our other file. This is our globular cluster. So this is my globular cluster over here. It's plotted these two things. So let us instead plot RA versus DEC. Okay, so this is how it looks as RA versus DEC in the sky, right? But in this one, we have not scaled it to the sizes. There are ways of scaling it so that the size of the dot is proportional to the brightness of the star. But we won't do that now. This is over here. Now this is the region, and if I were to make a plot, I can, if I like a very simple example would be, is if I would like to do a graphics plot, and I would like to, for example, see how these stars are moving, right? So now I know what is showing how they are moving. It is there, you go to form. In form, there's a form which is this one, okay, which is, 1 minute. I'll go to this thing, I go to sky plot, and here when you see I've got it in the RA deck, and then I put it in the term of forms, you can see the forms. I can add a sky vector. So if I add a sky vector, you see we have an interesting thing which comes here in these columns, which you have over here. Over here, I can put, just this thing, this. I can put over here. We'll talk about this later, but proper motion RA is the movement of the star in RA in terms of proper motion. Proper motion deck is the movement of the star in terms of deck. And so you can see this is the velocities of the star, right? But you can obviously that this is a real mess. So let us go like this, right? Let us reduce the size of these things. If I were to make a proper motion plot of these stars, that is, I take them over here and I plot them in terms of proper motions. you would see that this is the blob I get, right? So this is how the stars are moving in proper motion. Now you have to note that if you had a random set of stars, then they would have centered around 0, 0. Okay, 0, 0 would have been the center if this was not a globular cluster. But you can see that this center is somewhere else. We can see the coordinates over here. I'll just show it to you. Uh, yeah. So if you look at this center over here, you can see the coordinate down here. This is coming to you over here as minus 0.1 and minus 2.6. But random stars, I'll show that to you also, which are not members, they would have a different kind of spread. They would be around 0, 0. So these are basically cluster members. And I will prove that to you in the following way. If I want to draw, there are different ways of doing subsets in Topcat. You can, for example, through this plot itself, I can do a blob subset in the sense I can just mark this part of this, right? And I can say that this is my finished drawing blob, and I can call this my cluster, which is this blob, right? The other way of doing subsets in Topcat is using this. You can use this, and here you can actually give a function. For example, you can say a new subset T2, right? This is one which has, supposing we saw, right, proper motion in RA was, we saw it was minus, how much did we get? We got the center of it to be minus, we got the center to be here. We got the center to be minus 0.1 and minus 2.6. So I can say it is greater than 0 and less than 0.15, for example. And I say that my RA deck is greater than minus 2.5 and RA deck, sorry, not RA deck, PM deck is less than minus 2.7. So here I've actually put conditions. If I put these conditions, now you can see over here is I've got a smaller section. Here you can see subsets, and I've put another section which is my C2. So this is C2, right, which is over here. So so I can see this one. So there is the C2 part, and you can see this plot over here. But 1 minute, I just want to check something. So I'll just go in for this thing. And I think we have a double plot over here, probably. I need to have this window a little bigger. And so I will, yeah. So let me make another plot only. That would be better. I can do this, and I can get this one. Yeah. So here what happens is, you can see I'll do another plot. Yeah. Okay. You can already see this over here. If you look at this, I hope you can see this very clearly. You can, I'll try to make it a little better by doing this. I will make, you see the background stars. I've made them. Why is it not doing it? You can see the background stars are red in color, right? And these stars, the ones that we define to be our cluster members, yeah, you can see this over here, are the blue stars. These are the C stars. These stars are C2, which we also defined. So you can see these are the C2 stars, which are approximately the same. So you can see that the stars which are C2, they are clearly having velocities in the same direction. While the other stars, you can see like this light pink or whatever this color is, these stars have velocities in all directions. So we have successfully managed to find our members or stars which are probably belonging to this group because they are moving in the same direction with the same velocity. Now, if they are members of the group also, we should also notice in terms of their distance. We spoke about parallax. So if you actually see in these stars, you have a function where you have a parameter called parallax, and parallax is the distance, right? So you can clearly see that for these stars, if I take my subset C, you can clearly see that these stars which are subset C, they have a peak not at zero. All the stars have a peak close to zero. This one has a peak somewhere over here, right? And if we actually see that over here, you can see that the peak for C2, the parallax peak, if we see it in terms of parallax, the peak for the C2 stars is coming over here. Let me say, I will recalculate. um, this one is this. So I take this and I take for C2. Why is it not doing this? I'll say recalculate. I'm sorry, but this is the Windows version of Topcat, and that's why probably it's creating me problem. But over here, you can see that these C2 stars, they clearly have a different this thing. So you can see that the peak of this is coming somewhere over here. And it's coming over here. And this will be my approximate peak at which you're having this thing. So you can see that this is approximately coming somewhere over here at 1 point, at 0.9 or something like this. So these are stars at a fixed distance over here. Now you can see that there are stars in these other regions also, and these are probably contaminants, okay, which are moving with the same velocity but do not belong, right? So I briefly actually showed you all these steps of the analysis for M3. I will try to write it down in terms of a document. And what I want you all to do is I want you all to actually try and run this thing for M3, because next Saturday, when we have Mark Taylor with us, I would be happy if we have some level of understanding with which we can ask him questions which are not so basic, but a bit more, more challenging, right? So now I can see a whole set of questions. Error bars and graphs can be shown in Topcat, and you can check it out and do it. So Hasibul says that he's worked on determining parallax of Pleiades by using Topcat, but didn't get the proper motion plot as well as the parallax histogram. You need to try it out again. I'll try to write down the steps in doing it. Rohit is asking me why not the stars of a cluster centered around 0, 0. That's basically because 0, 0 means zero velocity, right? So in principle, if you pick up a random set of stars which are moving in all directions, then the average of that should come around 0, 0, right? So if you had a random part of the sky, right, which are not stars belonging to a certain group, but they randomly are oriented in different directions, then your center has to come around 0, 0, because those are stars which do not belong, right? If you want, with this one, what is happening is that because we've taken M3, which is a globular cluster, in globular clusters, contamination is much lesser. I will take another example where I can show you, for example, I'll take the Pleiades one only, which was taken, where you can actually clearly see, that there is the 0, 0 is actually what we call the field stars, or the stars which do not belong to the cluster, right? Oh, my spelling of Pleiades is probably wrong. Pleiades. I forgot the NGC number for Pleiades. I'll just tell you the NGC number. And you give me the NGC number. Or let's just take any other catalog. Let's take another cluster. This is an open cluster called NGC 1960. And if we try to resolve it, we'll get it over here. Now let me just resolve it, say in 20 arc minutes. Okay, it's okay. So I'll show you another cluster. This is a cluster called NGC 1960. And this is an open cluster. In M3 case, what happened is we had lesser stars around 0, 0 because it's a globular cluster. Globular clusters has a lot of stars, and therefore the contamination of field stars in globular clusters is very little, right? But if you have open clusters are far more open in the sense they take a much larger region of the sky, I mean, they are they spread out much more, and the amount of contaminants in it are larger. So now I'm downloading the NGC 1960 data, and I will show you that if we do the proper motion plot for NGC 1960, you'll see a good amount of stars around 00, right? But this thing is taking a bit of time. But you all should try doing this yourselves so that you can download your own data using Topcat itself, right? Like I told you, there are many more ways of also downloading data. Topcat is not the only way, but it's a very convenient way, especially like now in our case where we are trying to work on Topcat, then we can see this. So Rohit, that's the reason why they're not centered around 00, because they belong essentially to the globular. If like now we'll see in 1960, you'll see a larger number of stars around 00 compared to the position of the cluster. M45, yeah, you can use any globular cluster or anything like that, or an open cluster, because all of them get defined by this thing. So here's my 1960, and I will show you 1960 over here, NGC 1960. And with NGC 1960, what you can see is that here, if I were to plot your proper motion in RA versus your proper motion in DEC, you can see, yeah, you can see very nicely over here that around 00, you see this thing is surrounded, it's about near 00. Look at the around 00, you're getting a nice, the center of this distribution you can see is around 00, close to 00. It's slightly shifted, and here is a blob. This is the blob which belongs to the cluster. This blob is all these random stars which have random velocities in all different directions, and therefore you can see that in the 00, it's slightly off 00 because there is a cluster. If there was no cluster present in this field, then you would get a perfect 00. But here you can see I have this thing, and here this is the blob, and this is the blob which belongs to the cluster. So again, I'll repeat the same thing. I'll draw the blob subset. I'll draw this blob subset over here, right? I finished drawing the blob. Let me call it C, right? And now what I do for 1960, I will draw again another sky plot. I draw the sky plot, okay? And when you draw the sky plot, let us now put the form. In the form, you take the one which has the sky vector. And when you take the sky vector one, you'll see over here, I'm going to take proper motion RA, and here I'm going to take proper motion DEC. Yeah. Again, you'll see this thing going haywire. All you got to do is just reset this parameter, which is called scale. And here's your scale parameter. So you reduce your scale. And here, when you see go to position, this is the thing. See the subsets. These are the subsets. Let us go on to C, which are cluster things. I will recolor this thing to be yellow. And you can see that the blue stars, these are the stars which we defined to be for the cluster. And that's why they're all moving in the same direction. They have to do that anyway, because in the proper motion plot, we selected on them on the basis of their proper motions, right? So they have to follow this behavior of being like this. And similarly, in terms of distance, since all of them are at the same distance, if I were to make a histogram in terms of parallax, right? In terms of parallax, I'll get them all peaking at about the same region. So you see this peak is different. This is the peak for all the stars, but this is the peak which I'm getting for my cluster members, right? So I can look at this peak. I can also do this. I can take the stats. See here, you can take stats for a subset. So if I take a stats for the C subset, you can see for C subset, my parallax is coming to be 0.807. So I'll just jump a little bit and show you that if I use a calculator, and this is coming to be by 0.87. So if I want to find out the distance, I can find out the distance very simply by taking a calculator. And remember that we saw the parallax was coming to 0.82. The parallax for Gaia data is in milliarc seconds, and therefore I need to do 1000 divided by 0.82. So this is the answer. So this is giving me the distance to this cluster in parsecs, which is 1219 parsecs, right? So as your homework, what I would like you all to do for in preparation for the class on 22nd is install Topcat, play around with it, try plotting all kinds of things that you can get with it, right? And you do the proper motion plot, separate the members from the rest of the stars, and find the distance to the cluster. You can do it for Pleiades, you can do it for NGC 1960, you can do it for M3, do it for at least two different objects, and these should be clusters. Okay, don't pick up a galaxy, because for example M51 is not a globular cluster, it's a galaxy, right? So you need to pick up some clusters, some star clusters, either globular clusters or open clusters, and use the proper motion plot to find out the distance to clusters. So I will write this down in the homework section with the steps, okay, and you all can do it. Yeah, so yes, Renuka Velu is asking me, can you get NASA data? Yes, you can get that. I'll show it to you. It's very simple. Again, you use the same. For example, you can use your cone search. Go to VO, go to cone search, and instead of saying Gaia DR2, you just say HST, right? Okay, so now this is what it's going to show you, the HST data which is available, right? Oh, sorry, you do this. You say find services with HST data. I pressed, or you press this. Yeah, so to find a galaxy using distance to a galaxy using Topcat, the problem is to the galaxy, you will not get the velocities that well like you're getting it for clusters, because these clusters are within our galaxy, while your galaxy will be an external one, it'll be much further away. So you can do it if you, we can do something like that a little later. That is, if, for example, you identify, for example, Cepheids or something else, or a supernova in that galaxy for which you know the brightness, you can use that to find out the brightness. So that's a good idea. I can add that as one of the things for one of the science cases for distance to galaxy. Okay, I will add that, but I think we'll come up to that a little later. So now look over here. When we said HST, you can see here are our resources, right? So you can see this is a spectrograph. These are the guide star catalog. This is of SMC N888. So this is, so here what you're doing is you're actually getting it from, for example, this is M31, your 6 M31 globular clusters. We'll talk about this later. We have, sir, I think spoke to you all about VizieR. What this is doing is it's basically connecting to VizieR, and from VizieR, it's getting this data, right? So while you're seeing this over here, you can see it says associations, galaxies, H2 regions, associated galaxies, photometry, whatever. So you can actually use this for HST, find the object you want. For example, you're looking for galaxies. For example, we're looking HST photometry of sculptor dwarf galaxies. So you'll get it from here. So this is how you do it for HST. Yeah, so for all NASA missions, I think sir showed you all, but I'll show that to you again. We'll be talking about those also again. There's the problem is there's so much that we need time to talk to you all about. But for all HST missions, there is an archive called multi. Where is the? Okay, let's go to Google Chrome and look over here. And over here, there is this MAST. This is for HST. Okay. So this is a separate website, Mikulski Archive for Space Telescopes. This is run by the Space Telescope Science Institute. Okay. And they have everything which covers not only HST, but Kepler, KEPK2, TESS, various this thing. So you'll see over here where you can actually search for the missions. So you can get Hubble, JWST, they're already going to putting it over here. There's Kepler, there's Swift, there's TESS, XMM, there are various Galax. So all these data sources are sitting over here in this. Like I told you, this is not the only place they are there. They are there in many such locations. But one thing is like this. So you should directly go in for this. So for example, you go in for Hubble Legacy Archive. Yeah, you can click on Hubble Legacy Archive. This is a very useful archive. You can actually put, for example, in this legacy archive, Supposing if you're looking for, like it suggested, it's saying M101. You can actually look for M101, right? This is an object, a galaxy, and it's actually telling you the stuff, and it's telling you that for this thing it has all this data. Okay, and there are ways we will actually talk about it. You can go through it. The fits data is there, and it actually tells you which is the spectral, which spectrum is it. These are different filters on HST. What are the exposure times, what are the data, and many of these data sites even let you preview the data. That means you can see it before downloading it. It actually tells you the quality of the data. And yeah, so for example, if I take this, you can actually display it, and it actually shows you the data over here. Okay, so you can actually, yeah, so this is the part of the sky which is covered by this. You can expand it, look at it, and you can overlay also on this SDSS data, 2MAS data, various. We'll do a separate session on these data sessions. Is there any sense in changing the reading from RTL SDR to CSV and doing this thing for radio? It's just a matter of choice whether you do. But the thing is that the CSV is a much more generic data format. But FITS, for example, is specifically meant for astronomy, and therefore it makes things more convenient. So often to run certain, supposing this radio data, and if that radio data is being done essentially in another format, it is better to do it in that. But there may be limitations if you do it with CSV. So I don't know specifically about this thing you're talking about, but when you're dealing with astro data, even your files, it's far better to deal with FITS format, because FITS format includes everything that astro needs, right? While if you convert it to ASCII format or CSV format, it will work, but it will not have all the data. So VU actually decided that data should be in the form of what is called metadata. That means you even include the units and various factors like that. And many of them get included if you have your file in the form of a FITS file. But if you put it in another format, then it may lose these added data things which are there, right? So I would suggest that it's better if you're doing with Astro data, better stick to FITS format or the VO format. There's a VO format also. You'll see the VO table format. Those are better ones in that sense, but there is no hard and fast rule. So Justin, you can do whatever you can choose. If your procedures or modules are working with CSV, you can go ahead with CSV. There's no problem about CSV. I'll also repeat what Sir was talking about Python. Tomorrow we have our Python class again, right? We also I'll put a Google poll today that are there people who actually want Python from the basic level, right? If you all want Python from the basic level, then on another weekday, we can have these separate basic Python classes, because we don't want to disturb the Saturday, Sunday schedule, because you can already, I'll be soon be putting up a lot of your talks are already lined up. We already have a very tight schedule, right? So I'll put up a Google thing that who are the people who actually, or in Telegram, let me start the Telegram thing, and in that you all can vote and tell me how many people want basic Python classes. So then we can do a basic Python thing, right? Avik is asking me, is Topcat useful for only star prop? No, not at all. You can use Topcat for any data. It's like a spreadsheet, right? So you can use it for stars, for galaxies, for any data. You can use it even for non-astronomy data also. You can use it. There is nothing which stops you from using it. Like I told you, as long as your data is in an ASCII format, CSV format, you can upload it into Topcat and use it. So there's no such thing. Is Topcat useful for star properties or other large scale, this thing like molecular clouds? Okay. I think Sir mentioned it to you that visualization software is different. Okay. So one visualization software is DS9. I will list all the softwares. DS9 is one visualization software, which is very commonly used. Other than that, there is ESA Sky. Other than that, there is Sky View. So these are visualization softwares. So Topcat will not let you visualize. It will only let you handle data which is in the form of catalogs. Like I told you, data can be in the form of catalogs, images, spectra, different things, right? So Topcat will handle the catalog data, not the image data. So I'm sorry, but Topcat will not do this thing. Um, okay, Rohit Sachdev has a good suggestion. Mark Newman, computational physics. Yeah, so that would be good. I'll put up the Telegram invite, so then we can add all these resources and things like that. You can add it on the Telegram thing, right? Or does somebody else want to take up the responsibility of handling Telegram? Yeah, because I may not manage everything. Rohit Sachdev, will you take up Telegram? Will you handle the Telegram thing? Okay. Yeah. So then, because I want to outsource a little bit of the work, because so what you can do is start a Telegram group called Astronomy from Archival Data, right? And send the invite link. Send it to me, and I'll put it up on that website, so everybody can join that. Okay. Yeah. So homework for today is the Topcat thing, and I will write it down in detail on the website, right? So please, let's prepare for our next Saturday great event, which we have with Mark Taylor. After that, the following Saturday, we have somebody from Caltech, Luisa Rebul, who will talk about the infrared database, okay? So for that also, I'll give you all some homework, how to prepare for that. But let's first prepare for Mark Taylor Topcat, right? And please send in your Python assignments to the new email ID I've sent you, shrishtiastro2020@gmail.com, right? Send it in the form of a Python notebook so that we can directly run the notebook and check it out, right? And I think we are done for today. So thank you, everyone, and happy Independence Day again to everyone. And I think it's 11:30.
Thank you. So let's stop for today. And if there are questions or so, you can always
post them.
post
Is
them.
Topcat useful for rotational curve? Yes, if you have the what do you say, the velocity at different points in the form of a table, right? You basically need to have your data in the form of a table. Then you can actually use it. So Shrirang Sapte, yes, you can use it for this thing if your data is in the form of a table. But if it is in the form of an image, that will not help. You have to convert it into the form of a table, right? So, so